Alright, welcome back. So this one right here, we are going to look at calculating enthalpy changes, and we are going to go into how to communicate it once we actually calculate it. So what we have right here, remember, enthalpy change is what we have is delta H. So in order to calculate or to do one of these here, we need a few things. One of them is going to be molar enthalpy. So we need to figure out what substance and, of course, how much energy it's going to release per mole. Now, because we also need to figure out how much substance we have, we will need to know N. Now, we can get N from our balanced chemical equation, which we're going to look at later, or from the mass using our molar mass equation. So this one is going to be different right here, this balanced chemical equation, but that's going to be our first example on the next page, and I'll show you how to do it. The reason why we can use a balanced chemical equation is because the coefficients used for balance are molar coefficients, and they represent the ratio of moles required for the reaction to take place. So our formula for calculating, we got the change in enthalpy is equal to the number of moles times the molar enthalpy. So once again, this is an equation that you need to have memorized because equations are not given in Chem 30. So just remember, when we are communicating delta H and H, so change in enthalpy and enthalpy, if we have a positive value, this is for endothermic reactions. And if we have a negative, it is for exothermic. And same thing is that positive value means energy is entering something, negative means it is leaving. So you do need to be careful as well if we're referring to the system or the surroundings, but either way. Let's look at example 1. As I said, this is why we can this is what we can do to use the, in this case here, the coefficients. So it says calculate the molar enthalpy of combustion for oxygen given the following information, and we have our balanced chemical equation. Now, we see delta CH is equal to negative 2,856.8 kilojoules. So we know this is a change in enthalpy. But this number right here is for if 2 moles of ethane gas reacts with 7 moles of oxygen, producing 4 moles of carbon dioxide and 6 moles of water. This number right here is for the correct ratio for the balanced chemical equation. So we know our equation, delta H is equal to NH. Rearranging, we got H is equal to delta H over N. So we can take our delta H and divide by, when we look at oxygen, for this specific reaction, for releasing this amount of energy, we have 7 moles of oxygen present. So our answer turns into negative 408.1 kilojoules per mole. And how do we know it's exothermic? Negative delta H value, or it's a combustion reaction. Because we know combustion reactions always release energy. So that's how we know, right? We're calculating the molar enthalpy of combustion. If it's a combustion reaction, it should be negative. Now, this one's going to be a little different. It says find the enthalpy change when 5.50 grams of pentane burns. So pentane in this case, you can look at your data booklets, but it's going to be C5H12. Now, same thing, this time we're given our molar enthalpy, right? So we have a mass of pentane, we have molar enthalpy, and it's asked what is the change in enthalpy. So first thing that should be jumping off the page is the fact that we have a mass and not number of moles. So that's when, if you want to number of moles, you can just go down here, is equal to mass over molar mass, right? Our mass was our 5.50 grams. Molar mass for C5H12. I'm not going to show the calculations for it, because hopefully you guys should be good at calculating molar mass right now. But when you add up 5 carbons and 12 hydrogens, you should get 72.17 grams per mole. And that leaves us with the number of moles 0.076209 moles. So we can kind of don't worry about that and use our value for N down here. So our equation, delta H is equal to NH. So you go delta H is equal to 0.076209 moles times our negative 3244.8 kilojoules per mole. And we get a value of the change in enthalpy, negative 247 kilojoules, and because it's negative, this is exothermic. Now I know it doesn't say what is exothermic or not, but then again, that's just right there for you. All right, so that's just a different example there, how we use a mass given and a molar enthalpy to solve for enthalpy change. Now, example 3 is a little different as well. So when we look at this one here, we have when methane is burned, oxygen is consumed. Determine the mass of oxygen consumed if the change in enthalpy is negative 250 kilojoules and the molar enthalpy is negative 401.3 kilojoules per mole. So in this right here, of course, we need to get the mass. So our first step, need to get number of moles, and the second one, the mass. So I'm going to hold off. I'm going to let you guys pause this video and try the answer yourself, and just I'll give you a warning. So in 3 seconds, the answer's coming up. And the answer looks like this. So if you got half of this answer, you might have forgot that oxygen is a diatomic known as O2. So you need to multiply the molar mass of 16.00 by 2 to get 32.00. All right, so this is number one. This is one as well. It's like just knowing the units, knowing our equation, how to rearrange is going to be huge. Now down below, we have 2 old diploma examples. All right, so we have if 58.9 kilojoules of energy is transferred when 1.65 grams of ethanol, that's with an Al, CH3CHO, is burned in a calorimeter. Now I know we haven't came across this term yet, but it shouldn't matter what it's burned in, right? We know 1.65 grams of ethanol is being burned. So in this right here, the molar enthalpy of combustion for ethanol in the form of A decimal BC times 10 to the power D kilojoules per mole is going to be what? So we know we're given change in enthalpy. We can find number of moles. So you should be able to get this one. All right, same thing. I'm going to put the answer up in 3 seconds. So pause the video, give this one a try on your own. All right, so hopefully your answer should look something like this. Now, obviously, I have delta H here, 58.9 kilojoules, number of moles, mass divided by molar mass, and I get that. And of course, molar enthalpy, delta H divided by N. Now, you will notice that I get an answer of 1,572.8 kilojoules per mole. And you will notice that I can't put this inside my numerical response section. So I need to convert this into this form, A decimal B C times 10 to the power of D. So we take this, right? We know we have to move our decimal back 1, 2, 3 places. So we're left with 1.57281 times 10 to the power of 3. Now, you be careful for rounding as well, because it just so happens we don't really need to round here. So this is A decimal B C times 10 to the power of D, where my answer is 1573. And I don't need to round my 7 because there is a 2 right here. So just be very careful with your answers. So go 1573. And if that was a numerical response bubble sheet, that's exactly how I would record it. And last but not least, numerical response 4. Sorry, this is just old diploma question as well. All right, so with this one right here, same thing, pause the video because the answer is going up in 3 seconds. Like, give this one a try, all right? And here's the answer. So you notice I made a few adjustments here. So first of all, it says equation 1. So notice how I just completely scratched out equation 2 and 3 because I don't need it. It's only asking for equation 1. It's asking for the molar enthalpy of hydrogen. So I know this is a change in enthalpy. I know the number of moles of hydrogen was 3. So I take that enthalpy, divide by 3, and I get my answer right here. All right. So that is calculating enthalpy change. Now, same thing, you should be able to go to your workbooks and work on that section, because I think the last video was supposed to end with this, and I just forgot that it kind of went through, so whoops, sorry. So we're just going to jump right ahead to communicating enthalpy change as well, because we just spent all that time just calculating it. Now, how do we communicate it? That's our next section. All right, so with these right here, there's three main methods to indicate enthalpy change, or molar enthalpy. All right, so we're going to look at the three main ways to do it. And the first one we've already seen and we've already talked about. So this is the heat of a reaction is recorded outside the equation in our delta H notation. All right, so that's where we know if delta H is a negative, the system is exothermic. If it is positive, it is endothermic. So our examples, for example, if we want an exothermic reaction, we can look at the formation of ammonia. Now, I'm going to use these examples for all three here as well, so we get to see all of them and get comfortable with the numbers, so I'm not changing the reaction. Now, how we communicate that is exothermic, go delta FH is equal to negative 91.8 kilojoules. Now, for an endothermic reaction, right, now we need to make sure it is positive. So I'm going to take the formation of ethine and it would be positive. So we've seen these examples like this before. So nothing new here is that we take the delta H value outside the equation, and our positive and our negative will indicate if it is exothermic or endothermic. Now, method 2, we haven't really seen yet, or actually kind of had. If you think back to photosynthesis, so I'm just going to go back to that here now in a sec, or specifically this page right here, right, where we have enthalpy is positive and energy is shown as a reactant, whereas our exothermic energy was a product. We're going to use the exact same idea for this. So here we have, if a reaction is exothermic, energy is released, so it is written as a product. Where if it is endothermic, energy is absorbed, so it's going to be written as a reactant. Now, one little thing as well, because here we are using the sides, we never, ever, ever write a negative sign or even a positive sign. We just write them on the side of the equation that they occur in. All right, so for example, using our exact same two as well that we've done before, if we want to write, so our formation of ammonia, if you remember, that was exothermic, so we need to write the energy value as a product. So we would go N2 gas plus 3H2 gas produces ammonia, 2NH3 gas plus, in this case right here, 91.8 kilojoules. So the fact that we have it written on the the right-hand side as a product, now I know it is exothermic. Whereas my endothermic reaction, my carbon plus hydrogen, now I would write the energy unit on my reactant side, which is 227.4 kilojoules, produces my C2H2 gas. All right, so just the fact that we have it written on the reactant side, and here, product. So we've seen these before, now it's, right there in front of you. Now the last one is our potential energy diagram. So these are new, and you will see lots of potential energy diagrams, so please pay attention to what, how they look and how I show or represent them. So looking at our potential energy diagrams, now this shows potential energy for both reactants and products. So we get to see both things on our, basically it's a graph. So one thing that we need to remember is that if the reactants have higher potential energy than the products, it is an exothermic reaction, and we're going to use a downward arrow because the potential energy of the system is decreasing. All right, so if the potential energy is decreasing, that energy needs to go somewhere. In this case, it is going into the surroundings. So I'm just going to draw the example down here before I talk about the endothermic. So we know graphs will look like this. So we have our reaction kind of on the x-axis. We got potential energy normally in kilojoules on this side. Now, as we said, for an exothermic reaction, the reactants have a higher potential energy. So the exothermic reaction that we had on our previous slides was, of course, the formation of ammonia. So how this will look is that we're going to have a potential energy somewhere up here, and it's normally represented by a flat line. And for our formation reaction, we had N2 gas plus H2 gas. Now it says that we're dropping potential energy, so we're going to see a downward arrow like this and go somewhere the potential energy of our products. Just like that. So that is how all potential energy diagrams will look for exothermic reactions. Now obviously reactants and products will change, but it's always going to look like this. Reactants have a much higher potential energy. Now, if the reactants have lower potential energy than the products, this is going to be endothermic. So we're going to use an upward arrow because the potential energy of the system is increasing. So obviously, if we're adding energy to it, then the potential energy when we're done should be higher. So for our endothermic reactions, all right, there we go, look at that. So for our endothermic reactions, we're still going to have a graph, reaction on the bottom, potential energy on the side, normally in kilojoules. Now for our endothermic reactions, we're going to use the exact same one as well, is that we're going to start off somewhere and we have our products. Right, so carbon solid plus hydrogen gas. Now we're going to show an upward arrow this time because we're increasing, right? We're adding energy. That's the whole idea of being endothermic. We're adding energy. Whoops, sorry, that should be all straight lines. All right, so have a straight line. It's going to go up, arrow, and then we have our product, C2H2 gas. And all endothermic reactions are going to look like this because we're adding energy, so we're raising the potential energy. Now, to the last point, it says right here, the difference between reactants and products is the enthalpy change. So just because we're representing these as a graph, it doesn't mean we can't still find potential energy. So if you were to take the difference between reactants and products, so example, I'm just going to draw a straight line or a dotted line across here. So if you took the difference between the energy of the reactants and the energy of the products, we would get the change in enthalpy for this one, which is our negative 91.8 kilojoules. And same thing, if you got the potential energy difference between reactants and products here, right, so just draw a straight line across, we would get a change in enthalpy of the exact same number we had so far. It would be a positive 227.4 kilojoules. And that is how we can communicate the enthalpy change. All right, so really the only one we haven't seen so far is these potential energy diagrams. So the quicker that you can become familiar with them, the better. Now, of course, we do have some questions on the next page and our old diploma problems as well, right? Some old diploma ones. So on the next, technically 4 pages, there's questions, all right? So what we have right here, this example, you're using express the enthalpy changes for cellular respiration for photosynthesis using the 3 different methods of communication that we just went over. So for A, we're doing it for cellular respiration, and B is photosynthesis, right? So remember, A is writing in our delta H notation, where we take the delta H and write it outside the equation. Our second way is writing it inside the equation, and our third way is, of course, our potential energy diagrams. And the next few pages as well, you will notice that there are a bunch of questions like another example here, another example here, and of course diploma question, an old diploma question here, and another diploma question here, where we talk about, you know, actually seeing the diagrams, and boom, even another one here, right? Where we have 200 kilojoules energy observed in a reaction represented by equation 2. What is the mass of CO2 produced? So we're still using this one right here, specifically equation 2, so you cannot even worry about equation 1 whatsoever. Now, I can't remember if the notes, if this is equation 1 or 2, but just make sure it does say equation 2, right? That's the only way to solve this one. And same thing in the notes. Ooh, right, here's where the mix-up is. So this should be equation 2. So make sure to make that adjustment in your notes as you're going through, and then try to solve, okay? Now with these here, once again, it's just good for you to kind of dive right in and try them out. But if you want to check your answers for all these here, you can check on the notes on Google Classroom. The answer keys for all these will be up, so please check them, but make sure to try them first. Try them, then check your answers. If you get them wrong, figure out why they're wrong. And if you can't figure out why, send me an email, and we can set up a Google Meet or something and talk it over. But anyway, that's it for this lesson. And the next one, it should be on something called calorimetry. So, see you guys later.